So why is BJT biasing necessary? So if you see, say this is a microphone, okay, and I want to take the microphone's signal and maybe put it to a speaker so that everyone can hear it, right? So this is a classic example of amplification, that we take microphone's signal and we amplify it, and then we put it to the through the speaker so that it reaches to the people. So how it is normally done? So if you see that, if I simply take a microphone and I connect it to the BJT base. So why base? So this, I'm giving a quick summary, okay, because I have covered all these things already. So normally what happens is, if you want amplification, you in for active region, you have to take it in common emitter configuration, in which the input is given to the base. Input to the base is given, and output is taken from the collector, so that you get a amplified output. And the condition is that the transistor, so this configuration where you give input to the base and take output from the collector is the common emitter configuration, and for working it as an amplifier, you need to bias it in the active region. Biasing in active region means that your VCB should be greater than 0. Okay, so VCB greater than 0 means VCE should be greater than VBE. So I'm considering that you already know these concepts. Okay, so VBE is this voltage. We will look into this voltage, VBE, and this will be VCE. And this is for NPN transistor, right? For PNP, it's just a complementary to it, or the opposite to it. Okay, so having said that, we come to this configuration where we have actually made a connection in this manner. Okay, so now you see that I have directly connected this point to the VCC line. That means I'm directly giving base voltage from here. Now what will happen? What will happen is that this microphone signal, whatever small signal which is coming from the microphone, that will get absorbed in the VCC, which is actually a power supply, which is actually a stable power supply, right? So this is actually a stable power supply here, 2.5 volts. So whatever signal comes out will go through this shorted path to the power supply. And what will happen, that the base of the transistor will not get anything. So this is the importance of biasing. You have to properly bias your transistor in such a way that it has to be in active region, and a particular configuration, say common emitter, common base, or common collector, that depends on from where you are putting the input and where you are taking the output. Okay, the common emitter, common base, and common collector, that is defined by your input and output. Okay, now the thing is that the biasing will be needed in any kind of configuration. Okay, and the biasing will make sure whether the transistor is in active region, or is in saturation region, or is in cutoff region. Okay, so with this, let me go to the biasing techniques. So how do you bias a transistor? So biasing is nothing but putting proper DC voltages to your transistor so that it is biased in one particular region. I hope that is clear. Okay, so if I write what biasing is, this definition is not needed, but still I am writing. So biasing is nothing but putting proper DC voltages to the nodes of the transistor so that it remains in the desired region of operation. Okay. Now, what are the biasing techniques? So what we will do today, we will see the biasing techniques. First we will see for an NPN transistor, then we will see for PNP. Okay. So in gate, if they have to make a bit of difficult paper, they will give you PNP transistor, because normally what we solve is NPN and we are accustomed to NPN. It's just like saying we write with right hand. Most of us write with our right hands. So if we ask you to write with left hand, you will face difficulty. So it is just like that. So with NPN transistor, we are very much familiar. We are very much used to solving NPN transistor. But whenever in paper they give PNP, what we do, some of us will be very much scared. Okay, so we will see how to easily solve PNP without getting confused. Okay. So first, but we will in detail we will study the biasing technique for an NPN only. The same biasing techniques apply to PNP as well. Okay, there is no difference. So the first technique is simple biasing. Okay, let us simply try to bias the transistor. Okay, so how do I simply bias? So first what I had done, I had connected a direct connection here, right? I have made a direct short. Now instead of a direct short, if I connect it through a resistor, what will happen? If I connect it to a resistor, then the possibility will be that some of the current will go through this path. So this is now very dirty. So now suppose if I now connect a resistor here, then what will happen? This small signal, depending on whatever the value of resistor is, this resistor RB. Okay. So the small signal that is coming out from the microphone, depending on the value of RB, if RB is very large, then it will find hindrance moving towards RB, right? So most of the signal will go to the base of the transistor. Okay, so this is the basic idea of simple biasing, that you put a resistor such that the base is also biased and the microphone signal completely can go to the base of the transistor. It should not go to the power supply. Okay, so let's start with the simple biasing. So what we will do, we will put KVL equations and we will try to solve it out. Okay, so we will see what is IC, what is IB, what are the conditions we need to follow for active region of operation. Okay, so again I will quickly summarize the way I put KVL equation. Okay, so this VCC, whenever it is written like this, okay, this same circuit can also be drawn in this manner. Please don't get confused. This circuit and this is the same. Here I have just put VCC to this line. Here I have just taken a node out and put VCC. It means the same thing. The same thing is this as well. If I now put it like this, if I put a source in this manner, this is also the same thing. Okay, I'm quickly revising it. Okay, so please don't get bored if you know all these things, because I don't know your knowledge level right now. So I'm just quickly summarizing. Okay, so remember this polarity. Okay, and whenever here it is minus VCC, let's say in some places you will see this is given as minus VCC. Okay, so this means nothing but, so if let me write it here, minus VCC. So this is the same as saying it is negative with respect to ground. So everything is with respect to ground. Okay, you see this source is negative with respect to ground, right? And you see this source is positive with respect to ground. Okay, so if something is given to you in this manner, it means nothing but this. Okay, it is the same thing. Okay, so now I have this circuit with this VCC all over and this is ground. Okay, let me take this as ground. So if you want to draw, I can give you some time, or it's okay, right? Okay, so whenever if you want to write something and I'm going fast, you can interrupt me in between. Okay, and try to unmute yourself and interrupt, because I normally don't see the messages in the chat box. Okay, because I'm focused on this, so I might miss that. So just interrupt by unmuting yourself. Okay, so now you see this, that This is the simple biasing circuit. Now what we will do, let us put the KVL. Okay, so how do you put KVL? So please put the KVL. So this will be one path here, or this one, this is one path, and this will be another path, right? So one is this path, with orange I have drawn one, and the another one is this one, second. Okay, okay. So now what is this voltage? This is VCE. And what is this voltage? This is VBE. Okay, so now what are the two equations that you have? You have VCC equals to ICRC plus VCE, and the another equation will be, so this current is IB, okay, this current is IB, base current, and this current is IC. So the next equation is VCC minus VBE equals to IBRB. I hope you know how to put KVL. If you don't know how to put KVL, you can interrupt me now. I will tell you quickly. Okay. So now you have these two equations. VCC equals to ICRC plus VC, and VCC minus VB equals to IBRB. Okay. So now from here what I can write? I can write both the currents equation, right? I can get IC from here. I can get IB from here. Okay. So now what is IC? IC is VCC minus VCE by RC, right? And what is IB? IB is VCC minus VBE by RB. Now you have to remember that in gate you won't be asked to derive things, right? But you will get a circuit like this. You will get a circuit like this. There will be parameters, and they will ask you to find something, like they will ask you to find the value of RB or RC to keep the transistor in the, let's say, saturation region or active region. In gate, questions like this will come. Okay. Now, one second. Yeah. So now the next is, you will see that for active region, so we are now solving for active region because we are talking about amplification. Okay. So for active region, IC will be equals to beta times IB. Beta is the current gain. That beta will be given to you. Okay. So beta times IB. So I can also write that IC is equals to beta times VCC minus VBE by RB. You see. So if I put equation number, this is equation number 1, this is 2, this is 3, and from 2 and 3 you can come to this equation 4. Okay. Okay. And therefore, for keeping it in the active region, what should happen? So what should happen is VCE should be greater than VBE for keeping in active region, for keeping the transistor in active region. Okay. So now what is VCE? From equation 1, VCE is nothing but VCC minus ICRC. You see, from equation 1, VCE equals to VCC minus ICRC. So now I am simply going to put it. So what I am going to do? VCC minus beta times VCC minus VBE by RB into RC. Okay, this should be greater than VB. This is my condition. Okay, so from here I arrived to this condition. Okay, so this is the condition to be fulfilled for simple biasing. Okay, so I am revising one more time. From where did we start? We started from here. Okay, I had a simple biasing circuit, a circuit with simple biasing. Simple biasing means you simply connect a resistor RB, okay, simply connect a resistor RB from VCC to base, and from here, therefore from here the base is getting a current. Okay, and this current is nothing but IB, and this current is IC. And therefore you have two equations, two KVL to fulfill, because there are two paths, right? So one path is this one, this is one path, and the another part is this one. Okay, and therefore I am writing two equations, VCC equals to ICRC plus VCE. Okay, and the another is VCC minus VB equals to IBRB. Now from here I have written the equation for IB. Okay, I have written IB in terms of these things, and IC is also written, but it is not needed, we will see later. So IB we have got, and we know that IC equals to beta times IB. So I just multiplied this entire equation with beta, and once I multiplied I got equation number 4. Now I know that for active region I need VCE to be greater than VBE, and therefore I have written VCC minus beta. So from where I have gotten this? Because VCC I know is this, VCE I know is VCC minus ICRC. IC I have found out here from equation 4. So I have come to this equation. Okay, so please have a note on this. Okay, please ignore whatever is in the sides, we will go to that, but have a note on whatever KVL equations I have written. Please take a note of this. Okay, and after this I will tell you, we'll go through an example, and then I will tell you what is the problem with this biasing. Okay, so please take a note. Okay, so if it is done, then I will go forward. Is it's done, or are there any doubts? You can be very frank and ask questions. Okay, feel very free. Feel very free to ask questions, and please tell me when you are done. Okay, because I'll be waiting. So are there any doubts in whatever I have done till now? Any questions in this biasing technique? So why are these biasing techniques useful? So when in practice, when you are going to take a BJT and you are trying to make it work as an amplifier, then you will have to bias it first with DC sources, and after it is biased properly with those DC sources in place, you put the AC signal to it. Okay, and therefore you see whether you are getting an amplification or not. So if this is done, I will move forward with an example.
Done.
Okay, so now this bias is more sensitive to VBE variations. Why? We will see it through the example. We will see. Okay, okay. So find the collector bias current. Please note this question. I have given you beta value 100. IS is given as 10 to the power minus 17 ampere. Please take out your calculators, because I expect you to solve it with me. Okay. So now VCC is 2.5 volts. You know how to do it, right? You have to put two KVL equations. But before that, there is VB value not given, right? So whenever in your question in gate, it will come in two types. First, they will either give you this IS value, which is the saturation current of the BJT, or they will give you VB. So please note that either IS or VB will be given. Now if IS is given, it becomes a bit tougher. Okay, so how? So this is VBE, right? So first I will have to now find VBE, but IC is also not there. And what is the relation? The relation is VBE equals to VT natural log IC by IS. Now you see IC is also not present. Collector current is also not given, right? Collector current is also not given, and VT you can assume. So VT you take 26 millivolts. So even if it is not given, you can take VT to be 26 millivolts. Okay, but you cannot assume VBE. If IS is given, you cannot assume VBE, right? You will have to find it out. So how you do it? The method to solve this kind of problem is, you first make an assumption. So first step will be assume VB to be 0.8 volts. Okay, first you assume VB to be 0.8 volts. Now once you have assumed VB, you know that this is the path. There are two paths, right? So you know that this path is having IB current, and I have assumed VB. So what is IB? IB is VCC minus VBE by RB. Okay, so now this will be nothing but 2.5 minus 0.8. I have assumed VB by RB is 100K. So now, just now I told you that you cannot assume VB if IS is given, right? So we will see why I am assuming it right now. We will see that, okay? So now IB is given as this. So you see that since there are two unknowns, you cannot move forward without any assumption, okay? So IS is given, IC is not there, VB is also not there. So I cannot use IS and VT to find any of the parameters. So what I will do, I will first assume 0.8 volts as VB. I will find the value of IB, okay? So quickly tell me, what are you getting? 2.5 minus 0.8. This is in volts, this is in kilo ohms. So what you are getting is 1.7 divided by 100 milliamperes, okay, or 17 microampere. This is your IB. Now what is IC? IC is beta times IB. Beta is 100. So 100 into 17 microampere will give you 1.7 milliampere. Okay. Now what you do? Now you use this equation. You use this equation. Now you will say, what is the use of using this equation, ma'am? You have already assumed VB. So why are you using? We are using it to verify and iterate. This is called an iteration process. Okay, this is how you actually do it. So what you do? You take this equation and you find VB. 0.026 is volts, is VT value. Natural log, please remember this is log base E, not log base 10. Don't use log base 10. Ln is log base E. 1.7 milliamperes, so I am writing into 10 to the power minus 3 upon 10 to the power minus 17 was IS. Okay, so what are you getting? 0.026 into natural log of 1.7 into 10 to the power minus 3 upon 10 to the power minus 17. 0.852 volts. Now you see your assumption was 800 millivolts, right? What we assumed was this 0.8 volts, and what you are getting is this 0.852. Now what you will do, you will take this 0.852 and you again find IB. What you get? 2.5 minus 0.852 upon 100K, right? Now what you are getting? You will get 16.5 microampere, and this will make IC as 1.65 milliampere. Okay, so this is with this value of VB, and this was with the assumed value of VB. So assumed VB, calculated VB. You see there is not much difference, not much margin of error. So now you need not iterate it anymore. Okay, and after this one iteration, you see IC is 1.65 milliampere will be your final answer. Okay, in case VB is not given, this is how you should proceed. Okay, and this can be a numerical answer type. If it is a optional question, if options are already given, they will not give you two options to confuse. They will not give you 1.7 and 1.65 because both of them can be correct. They are very near to each other. And in numerical answer type, they will definitely keep the margin. They will take the answer to be suppose 1.6 to 1.8 or something like that. They will do. Okay, so it will anyways be correct in that case. Okay, so now you see what is the value of VCE we are getting, because this was a biasing problem, right? So VCE will be VCC minus ICRC. Okay, VCC is 2.5. What is the value of RC? RC was 1 kilo into 1.65, and as I have repeatedly told in my previous classes as well, I take all the units to be like resistor, I take it in kilo ohms, and current I take it in milliampere. So automatically the voltage will be in volts. I did not make any changes, any into 10 to the power minus 3 or something. Okay, it automatically will come. So 2.5 minus 1.65 will give you 0.85. Now you see VCE 0.85 volts and VBE what we got after calculation 0.852, right? And I have said that VCE should be greater than VBE. So you see that they are actually approximately matching. They are, it is not greater, right? It is not greater, but it is approximately matching. That means this transistor with this biasing values, with the this resistor values of RB, RC, beta, VCC, with these values, this transistor is in edge of saturation. It is not in active region, it is in edge of saturation. Okay, so quickly just see whatever I have done and then I will move forward. It is not yet finished. Okay, the example is not yet finished. I want you to just summarize whatever I have done. Okay, so beta value was given, IS was given. I told you that if IS is given, you will have to use this formula, but IC is also not given. Okay, now what we do, we assume VB to be 0.8 volts and we know the equations. We know IB is equals to VCC minus VB by RB, that we know, and we will just put the values. When we put the values, we got IB as 17 microampere, IC will be 100 times of IB, beta IB, and that we got as 1.7 milliampere. These values are when VB is assumed to be 0.8. Okay. Now with this value of IC, we are again trying to find what our VB is, so that we can know that whether our assumption was near to the perfect value. Okay. So what we do, we use this value of IC and the given value of IS and we try to find VB. We see that the VB is 0.852 volts, which is near around 0.8, right? So what we do, we try to find the value of IB with this VBE and we see that IC and IB come very much close to the previous value which was assumed. Okay, and if you keep on iterating now, if you now take this value of IC and again find out VB, you will see that it keeps on iterating and it keeps on going towards 0.8. The margin of error will keep on decreasing as you keep on iterating, but after 2 iterations you don't need it actually. Okay, so VCE is VCC minus IC RC. Now we found out VCE and we had said that we have to make the biasing as such VCE should be greater than VB. But we are seeing that in this case VCE is approximately equal to VB, right? It is loosely equal to VB, it is not going greater, and therefore the transistor is in edge of saturation. So is this clear till now? Should I move forward?
Yes, ma'am.
Okay. So now let us see that what can I do to keep this voltage. So basically VCE minus VBE is what is VCB, right? And for keeping the output in reverse bias, we have to keep VCB greater than 0, and that's why we said that VCE should be greater than VB. Okay, so now I am saying, yeah, so now I am saying that suppose VCE minus VBE, that this difference okay, is 200 millivolts. Now, how the question can be asked? The question can be asked as what value of RB, provides a reverse bias of 200 millivolts. This is the question. So this is now a 2 marks gate question. Okay, because this is now creating a twist in the problem. So from where did we start? We started from a normal self bias, a simple bias circuit. We saw how to assume VB and we saw how to get IBIC. Okay, and then now I am saying that suppose I want a reverse bias of 200 millivolts. What should the RB value be? Because RB will control it, right? How will RB control it? You have seen the equation. You have seen that IB equals to what? VCC minus VB by RB. Okay, and this RB's value is what is controlling IB, right? And IB control, if you multiply beta, you get IC, and from IC, VC is related. So then there is a relation between VC and VB. Okay, so what will happen? What I am saying? I am saying what value of RB provides the reverse bias of 200 millivolts. That means I am saying that VCB is 0.2 volts. What I am trying to say is that earlier in the problem where we saw that VC is 0.8 and VB is 0.852, I was saying that you know what, there is no margin here. It is in edge of saturation. There is no margin here. But now I am saying that I want a margin of 0.2. That means now VCE minus VB will be, so what value of RB ensures that? What value of RB ensures that? So once I have this, how will I solve this now? Anybody? So now again, you know that earlier you have found out VB to be 0.852. You use the same value. What will you get as VCE? VCE will be 0.852 plus 0.2, right? That is 1.052 volts. Now once VCE is 1.052 volts, VC is nothing but VCC minus IC RC. RC is fixed. So this is 1.052, 2.5 minus IC into 1K. From here you get IC. IC is 2.5 minus 1.052. Okay, this is 1.448 milliamperes. And if this is 1.448, then IB is what? 1.448 by 100, giving you 14.48 microamperes. Now once IB is 14.48 microamperes, you know RB is VCC minus VB by IB. 2.5 minus 0.852 by 14.48. This will give you 2.5 minus 0.852 by 14.48. This is giving you, this is in microamperes. Sorry. Okay. So this is in microamperes. So this will give you 113.8 kilo ohms. Okay. So Chandrasekhar, you have joined late, but I think from next question you will be able to pick up. Okay, we have started biasing techniques. So those who were present right from the beginning of the class, is this clear whatever I have done, or should I explain it one more time?
Clear, ma'am.
Clear, right? So this is how the question can be framed. Okay, they can ask you in maybe in 2 parts also, they can ask you this question. Okay, so now you see that for simple biasing, as you change the value of base resistor, you will change the value of the base current, and therefore you will change the value of the node voltages as well. And therefore what will happen is that your biasing will increase, biasing will change, and therefore now what has happened with this, I have actually got a margin of 200 millivolts here, right, between my VC and VB. Now I am sure that my transistor will be in amplification region and it can amplify the signals, right? But earlier with 100 kilo ohm, my transistor was just in the edge of saturation. It was not in a very good amplification range. In fact, it would not have been, it would not be like, maybe it will not be able to amplify at all. Okay. So with this, the simple biasing ends. Okay, so one more thing is that last two sessions were missed. Okay, I was not well, so I missed last two sessions. So that I will be doing today itself. So today we started off at 4, so we will end at 5:30, and then from 6 to 7:30 I will take another session, and we will finish all the biasing problem, and we will also finish the PNP one. And after that, if time remains, we will do the amplification question. Okay, one or two interesting question we should do. So if you guys say, I can take from 4 to 6 and then from 6:30 to 7:30, or else 4 to 5:30 and then 6 to 7:30. So whatever suits you. Okay, so let's go to the second question now. So I hope this one is clear. Simple biasing. Now what is the problem with this simple biasing? As I had said that I will tell you the problem in simple biasing. So now you see, as the value of VBE is changing and the value of IC is changing, the entire region of operation suddenly changes, right? So if I change VBE, suppose if VBE is fluctuating or beta is fluctuating. So what happens if beta fluctuates? If beta fluctuates, IC fluctuates. So in both these cases, the range of the active saturation range, the BCB, is messed up, right? We just saw it, that I need to increase the value of RB if I need a 200 millivolt drop. So if I now suppose keep everything constant, and if I change beta, okay, then the IC changes, and IC changes means this value, because if RB is fixed and IC changes, and then IB also changes, and if IB changes, the variation is in VBE, right? And it will completely come out of your region of operation. So this, some points need to be noted. So now the points that I am saying, this can come as a theoretical kind of question. I think you guys now have true and false questions as well in GATE, right? Like multiple choice type. So it can come in that. So the first is the effect which is a problem in simple biasing. So I'm writing problems of simple biasing. Okay. So problems of simple biasing is that VBE uncertainty is very much pronounced. Okay, please write these points. It can be useful. Even if you are preparing for ESE also, then this is very much useful to it. Okay. VB uncertainty is very much pronounced because base current is determined by VCC minus VB, right? So see, you might not be able to remember everything, right, in GATE, but how you know? You simply write the equations in GATE exam, okay, and then from there you can come to conclusions for theoretical questions as well. Okay, so that is how I do it. I write equations, I try to understand the circuit, and then whatever theory question is also there, I can correlate with that. In ESE also you can do it, because in ESE there is a lot of theory, so you cannot remember everything, right? So you should remember how to solve the circuit, and you should remember the circuit. That will do. Okay. Okay. Now the another is, so this is very much sensitive. So very much sensitive to VB. Okay. Who is very much sensitive to VB? Simple bias circuit. Okay. Okay. Now the other sensitivity is IC heavily depends on beta. Okay, and this parameter, it can considerably change, it can change considerably with respect to temperature or device parameter variations. It is highly dependent on it. What are device parameter variations? When you will make a transistor on semiconductor level, when you make a transistor, a lot of things come into picture. Okay, so I'm not going into that. So a lot of things comes into picture. You can think it of like painting something. Okay, so if you mix more water into your paint, it will get diluted. If you mix less water, it will be thick. So depending on that, it will affect your painting, right? So just like that, when these devices are made, a lot of factors come into picture, and that can considerably change your beta. So but when you are making the circuit, what mainly changes your beta is the temperature, because current will flow in your in your transistor, and that will heat it up. Once it heats it up, the current will increase more. Okay, that you would have studied this effect. Okay, and finally it will lead to transistor burning out. Okay, so now what we will do is, we will try to minimize these two effects. So now you remember, in the entire biasing concept, what you are actually doing is, you are trying to minimize these two effects in the entire biasing theory. Okay, we will be trying to minimize these two effects. So biasing should be done in such a way so as to take care of VB and beta variations. Okay, basically beta variations that lead to IC variations. So we will be doing the biasing in such a way. So from here we now come to resistor divider biasing. So what we had done in simple biasing, we took a simple transistor RB and we connected it with supply. This was RC, right? Now what we will do, we will do a resistor divider bias. What we will do, we will make a resistor divider network instead of a direct RB. Okay, so now from here we come to the second problem of resistor divider biasing. Okay, now in the first part of resistor divider biasing, what we do is, we assume negligible base current. Now before I proceed, I will do some markings here. This current will be IC as usual. This is IB. This current is I1. Okay, and this current will be I1 minus I2, IB. Okay, and the total current will be what? Therefore, let us say the total current that flows here is capital I dash. Okay, so I dash is basically, so let me just write this as I2. This will be better, I think. I2. Okay, okay, so now I1 is actually this will be I1 only. I should not put it I dash. Okay, it is the same thing. So this current is I1, which is the main current entering, and this is IB, and I2 is nothing but I1 minus IB. Okay, now when I say that the first method of designing this circuit is that you assume negligible base current. So negligible base current with respect to what? I am not saying zero base current, I am saying negligible base current. So negligible base current has to be with respect to something. Okay, so if you say that I have a stick and this is a long stick, so this stick is long with respect to what? Because I can bring a longer stick, right? So comparison is always between two things. So when I say assume negligible base current, what I mean is that I1 has to be very, very greater than IB, at least more than 10 times. Okay. So if I make sure of this condition, then we are going towards solving the first method of resistor divider biasing. So the first method of resistor divider biasing, how they can give you in gate exam is, they will start with assume negligible base current. And when they say assume negligible base current, okay, then how you are going to do it? Okay. So when I assume negligible base current, I put this node as X, capital X. And what is Vx? Vx is VCC into R2 by R1 plus R2. Remember, this is not Thevenin equivalent that we normally study. So Thevenin equivalent we will go after this. So to solve resistor divider biasing, there are two methods. First is you assume negligible base current, you directly come to this equation. Second is the Thevenin approach that we will do later. Okay. So Vx we have got VCC into R2 by R1 plus R2, and I assume that VCC and VCC by R1 plus R2, which is nothing but I1, is very, very greater than IB. Okay, this is done. So now you see that Vx is VCC into R2 by R1 plus R2, and that is directly nothing but VBE, right? Vx is VBE, right? Vx equals to VBE. And therefore, IC is nothing but Is exponential e to the power VBE by VT. So VCC by VT into R2 by R1 plus R2. Is there any doubt here? Why I have written it like this? Why did not I write it in terms of IB? Because I told you IB is negligible, right? So how will I find from IB? If IB is so negligible, I am not trying to find it out at all. I can find it, but I am saying it is very low, you know. So even if you multiply beta to it, nothing comes out. I don't know how to solve that. So how I solved it? I solved it in this manner. So now our problem that VBE was depending on IB, and therefore VBE was depending on IC, and IC again was depending on VBE. So there was a cycle. So I have now broken the cycle. I have broken the cycle by assuming IB as negligible. Now you can say that, ma'am, how can you assume IB to be negligible? Well, I will make IB negligible. This is in my hands. I am designing the circuit. So I will choose R1 and R2 in such a way that this condition will get satisfied. VCC by R1 plus R2, I will choose R1 and R2 in such a way that my current that is going to the base will automatically be very, very less than what is flowing through R1 and R2. We will see it in the example. So till here is it clear that how we arrived at resistor divider biasing and how it will help us to achieve the goal of VB variation and IC variation. After that I will go to the examples. So till here is it clear? Any doubts? Then we will start the example. Okay, so I'm assuming you guys don't have any doubts. Okay, okay. So I think in next half an hour we will finish the resistor divider biasing. Okay. So now this is your question. Please note it down quickly and then I will start. And after noting down, please let me know that you are done. Please note it and then we will start. So I have asked you to find IC and note in the question, don't start solving. So we will see because some of you are joining in between. So I'll again tell you how to solve it. So again you see that I have not given you VBE. That means you will have to do the assumption part. Okay. So please let me know once you have finished writing the question.
Yeah.
Yeah. Yes. Okay. So please start with finding Vx. So this is Vx. So tell me what Vx you are getting. So now, so please start by solving for Vx and tell me what Vx you are getting. So I will not do the calculation now. You guys will do. So Vx was VCC into R2. Okay, into R2 by R1 plus R2. This I hope you know from where it is coming, right? This equation is nothing but the series resistor divider, voltage divider. This is voltage divider. Okay. Yeah, 0.8. 0.8. Vx is 0.8 volts. Right? Now please find IC from this equation. So you know that Vx is equals to VBE, right? Vx is nothing but equal to, so Vx is this voltage, Vx is this voltage, this node voltage, and this voltage Vx is nothing but VBE. I hope there is no confusion here. So when I say the voltage at node is Vx, so you can apply a KVL directly here. So minus Vx plus VB is 0. So Vx equals to VB. Okay. So please tell me what is the value of IC you are getting. Okay. What microamperes you are getting? Tell me in microamperes. Okay. IC, value of IC. Why is it taking so much time? Please solve it and tell me.
230.
Yeah, 230. I think you will get 231. Okay, if you take VT as 26 millivolts. Okay. 230 or 231 both are fine. Okay. So therefore IB will be what? 231 by 100. Beta is 100. 2.31 microamperes. Okay. Now, is the base current negligible? How do I know? I find VCC upon R1 plus R2, as I had mentioned that the main current, base current will be negligible with respect to main current, right? This is the main current, I main. So with respect to the main current, the base current has to be negligible. Okay. So what is the main current? 2.5 divided by 17 plus 8. How much is it coming? It will be in milliamperes, right? So it will be pretty high.
0.1.
Yeah. So 0.1 milliampere. So 0.1 milliampere and that is 2 point. So 0.1 milliampere is nothing but 100 microampere, right? So what is the ratio? 100 divided by 2.31, approximately 43 times. So I main is approximately 43 times IB. That means IB is negligible with respect to I main. And therefore now this is independent of VB variations, right? So VCE, if you calculate, you will get VCC minus RCIC, and this you will get as 1.345 volts. You can check it. Okay. And therefore VCE is greater than VBE, and therefore it is in active region of saturation. Active region of operation. And remember, that once you have taken IB to be negligible, if you have satisfied that condition, this will be inactive region. Okay, so this is how the resistor divider circuit. First method is that you design the circuit in such a way that you get the IB to be negligible with respect to the main current. So I'll quickly browse over it, just take a note of whatever we have done. After that, we will go to the Thevenin equivalent. Okay, this is how we had solved it. So quickly have a look. After I'll give you 1 minute and then we will start the next one. Okay, so let's start with the same problem but with the Thevenin equivalent analysis. Okay, so how did we solve the previous problem? In the previous problem, we started from Vx to Vb to Ic and then to Ib, and then we cross checked whether Ib is negligible, right? We did not calculate Ib first and then Ic, right? We calculated Ic first from the knowledge of Vb and Is. So this equation, which you will be seeing very much used less in the previous gate questions, in very few questions they have given Is and you have to calculate. So that's why it is more prominent that now this kind of question will come. Instead of direct Vb, you might get Is. Okay, so now again the resistor biasing. Right? Let me write VCC. Okay. So now I'm saying that I was unable to design the circuit where IB is negligible. So IB is not negligible with respect to I main. Okay, this is I main, this is IC, this is IB. Now if I say this is I main, this is IC, what is the current from here? That is I main plus IC. I main plus IC is what your power supply is sending. Okay, so now when this IB is not negligible, then remember these two resistors R1 and R2 are they are in parallel or they are in series? They are neither in parallel nor in series. Remember in the last question you had assumed IB to be negligible and therefore you could take R1 and R2 in series. There was no concept of R1 and R2 parallel. I directly took it to be in series and therefore I was getting the Vx as R2 by R1 plus R2, right? I took IB, I did not take IB as 0, I took IB as negligible with respect to I min. Okay, so now I'm saying IB is not negligible with respect to I min. That means I cannot take R1 and R2 to be in series. So how do we solve this kind of a problem? So anywhere in network analysis, you have a circuit, you can find a Thevenin or Norton equivalent that you have studied, right? That a linear circuit can be made into a Thevenin or Norton equivalent. So from where do we take Thevenin or Norton equivalent? We take from this point Vx. From this point Vx we will take it. So what is Thevenin equivalent? So first Thevenin equivalent has a Thevenin voltage and a Thevenin resistance. So we will find Thevenin voltage first. Now Thevenin voltage is nothing but the open circuit voltage from the point where you are finding the equivalent circuit. Okay, so Thevenin voltage is nothing but the open circuit voltage from the point of seeing. So this is your point of seeing. So from the point from where you are finding the Thevenin equivalent circuit. So here where is that point? Vx is the point. So what I will do? This is the open circuit voltage, right? So if this is your circuit, then this is the voltage I am talking about. So now you see the entire transistor circuit doesn't matter because this is already open. It doesn't matter, right? Because this is neither, it is not connected. So VOC, okay? So R2, R1, R2. So what will be VOC? Nothing but VCC into R2 by R1 plus R2. So it came as the same as the previous one. But in previous one, the reason was IB was negligible. But in this one, the reason is that it is the Thevenin equivalent. So please understand the concept. Okay. Please understand the concept. Don't mess it up. So VOC is VCC into R2 by R1 plus R2. And what is the Thevenin resistance? How is Thevenin resistance calculated? Thevenin resistance. Right? So Thevenin resistance is the resistance where VCC is 0. We turn all the independent sources 0 if you remember. Okay. So once you put all the independent sources as 0, what is happening? Now this is connected. This is connected, right? But this is ground. Now this is ground. Now the R1 and R2 are connected between two same points, right? This is same as saying like this R1 R2, is it not? And therefore your Thevenin resistance is R1 parallel with R2. Please remember this. Please see this very carefully and note it down. Okay, first note it down and then we will go ahead. I hope you are able to see this. I'll give you 1 minute. Just note everything down, look into the circuit once and then we will start again. Okay, so I hope you guys are done now. So now what will be the value of IC? IC will be, so how do we write the circuit? We rewrite the circuit like this. So we have found the VThevenin and we have found the RThevenin, and you would have seen, those who have studied it earlier, you would have seen that this is VC, RC, right? And instead of the resistor divider, now we directly write it like this. So this is RTH and this is VTH. And why do we write it like this? Because I have told you, right, that this is the circuit which we calculated the Thevenin of. So this part, this entire part, we make a Thevenin equivalent. And therefore I am replacing that. Replaced it with that. Okay. So once I have replaced it with this, what will be the value of IC? What will be the equation? IC will be IS exponential V Thevenin minus IB R Thevenin by VT. Now you see that there is an exponential dependence on VTH and RTH, right? And therefore any variation, any small variation in VTH or RTH, that will lead to a bigger variation in IC in intermediate results. Okay, so the iteration for this will go like, you will first find VB with ICI VBE, you will assume, you will find IB, you will find IC from there, and again from IC you will find VB, and so on. This is our iteration process. Okay, the same process will continue here as well, but we will see how the variations will come. Okay, therefore in the resistor divider model, with the proper choice of R1 and R2, as we had seen in the first method, with the proper choice of R1 and R2, you will automatically make base current negligible, and therefore the variation with respect to beta will be very low. Okay, but if you are not able to do that, then you see that there is an exponential dependence that will lead to bigger variations. Okay, so therefore the primary concern of using a resistor bias is that we try to make the main current very large with respect to the base current. Okay, so now we will repeat the earlier question with the Thevenin model. Okay, so the earlier question was this itself. Okay, so okay, not the earlier question, I will take some other values because I will have to make sure that R1 and R2 values are different. So please take this question. Okay, so RC will be 5K, this is 2.5 volts, this will be 170K, this is 80. So after solving this question, we will take a break of let's say half an hour or 15 minutes more probably. So after that we can join back in 6 o'clock, and then from 6 to 7:30 I'll take the next session. Okay, so okay, let's solve this question first. So how will you start? So let me tell you what is given. What is given is beta 100, same, and is 10 to the power minus 17. So how you start? You start, so see, directly for finding VTH you don't need anything, right? So find VThevenin and find RThevenin. Please find that and tell me what you are getting. You already have R1, R2. You find VThevenin and RThevenin. After finding, please put it in chat box whatever you are getting. Okay, okay. So we have first values as VTH 0.8 volts and RTH as 54.4K. Others have got it, right? I'm assuming you have got it. Okay, good. So now, what is the Thevenin model, equivalent model? I had told you, right? So this is the Thevenin equivalent model, this one, right? So this is 54.4K, this is 0.8. This is RC, which is given as 5K, this is 2.5. Okay, so now remember that you have not actually connected an external source and an external resistance. This model itself is behaving in this manner. Okay, this resistor divider is as if you have connected this thing here. Okay, and now what is VB? So now in the previous question you had assumed that IB was negligible with respect to I main, and therefore we did not find the Thevenin model. We actually did not need to find the Thevenin model. Okay, but here what we have done, we have found the Thevenin model, therefore VBE will now not be equal to Vx directly, right? In that case this was Vx, which is equal to whatever VTH you are getting here, and in that case Vx was directly equal to VB because IB was negligible. Okay, but here what is happening, VB is now equal to VTH minus IB/RB, and IB is not negligible. In that case IB was negligible. Okay, so this is VTH or Vx, whatever you want to say. You got it? Getting the point, right? So now RB you know, right? RB is nothing but 54.4. So let me write it the RTH, otherwise this will give you a confusion. Okay, so now what we will do, I have again two equations. IC is IS e to the power VBE by VT. And again I don't know IC, I don't know VBE. So we have to start with an assumption. Now in the previous questions you have assumed VBE to be 0.8, right? 800 millivolts. But you know here VB will be whatever VTH minus IB/RTH. That means it will be something less than 0.8. Is this line clear? Earlier we used to take VB as 0.8. But here in the circuit VB 0.8 cannot be fulfilled. Why? Because VTH is already 0.8, right? VTH I have got 0.8. So obviously VB cannot be 0.8. It has to be less than VTH by an amount IB/RTH. Is it clear or should I repeat? Okay, one of you has said clear. Okay, so VTH is 0.8 volts, VB is equals to VTH minus IB/RTH, and therefore VB cannot be assumed at 0.8. So let us say it is 750 millivolts, 0.75. Now can you find IB? How will you find IB? IB is VTH minus VB by 54.4K. Please put in the values. So 50 millivolts by 54.4K. Solve it. You will be getting 0.919 microampere. Please do it till now and then tell me. After that I will proceed. Is it clear till here? Okay. So now after this, so what we have done? We started with finding VTH, we found RTH, we assumed VB, we found IB from the KVL equation. Now what we will do? IC will be beta times IB. Now since IB is not negligible, I can use the beta. So 100 into 0.919. I am getting 91.9 microampere. Now with this 91.9 microampere, I will find VBE. Again, VT natural log of IC by IS. Okay, And this value, tell me what you are getting. You will be getting 776 milliampere, millivolts. Now your assumption was, VB assumed was 750 millivolts. Now you see there is a 26 millivolts difference. Now with this 776, if you put it in the KVL equation, you will see IB will come to be 44.1 microampere. Okay, and again from this 44.1 microampere, you will see VB, you will get 757 millivolts. And again from this 757, you will find, you will again get IB as 0.7, IB as, yeah, did I miss something? Yeah, sorry, this is this is IC. So this is 0.441 microampere. And from here you will get 757 millivolt as VB. I am talking about the iteration process. And IB will be equal to 0.79 microampere. So now you see that although the difference is not that much, 776 millivolts, 750, right? 26 millivolts difference. But IB is very half than before. Earlier the IB was 0.9, now it is 0.45. And then from 0.45, what VB you get is only 7 millivolts difference. But with that 7 millivolts difference, again IB is something else. So you see that the fluctuation is very high. That is because in the exponential term, your IC is entered. The dependence is now exponential. Okay, the dependence is now exponential. So remember, in the resistor biasing, you will have to carefully choose R1 and R2 such that the main current becomes very high than base current. And once the base current is negligible, then only this circuit will be get rid of the variations of beta and VB. Otherwise, this circuit will have this kind of an exponential dependence and your IC will be very much drastically increasing. Okay, so till here is it clear to you? Because of if you make the calculation, you will see that if R2 is 1% higher than its normal value, then that 1% error in resistor value will give you 36% error in the collector current, which is too much. Okay, so this is of very little practical value. Resistor divider biasing is not used directly. Okay, it is used with emitter degeneration, which we will do next. So for this circuit, for the emitter biasing, for the resistor biasing, resistor divider network, either you have to make it negligible. So the problem is that even if you make the base current negligible with respect to main current, if your resistor values change a bit, then the negligibility factor may go away, right? And therefore that is what I am saying, that if the resistor's value increases by 1%, the collector current increases by 36%, and that circuit might be out of the active region. Okay, okay, so please make a note of it. Please make a note of this, and please let me know if you are comfortable with again the class at 6 to 7:30. So we will finish the last biasing and then we will finish the PNP biasing as well. So please put it in the chat box if you can. Will you be able to join from 6 to 7:30? Okay, so do you guys have any other class from 6 to 7:30? Okay, so okay, okay. So even if one person is attending, I will take the class. Okay. So the same link you guys can join from 6 to 7:30. Okay. So if you have noted down this question, then I will log out from the meeting. Okay. So okay. So then I am logging out from the meeting. Okay. So let's join back in the same link at 6. Thank you.
Thank you.
Himesh, you are saying you joined late. So there is no PDF of this lecture, but the recordings are going to the NPTEL office. So they will make it available later. Okay. So we are not supposed to make it public right now. Okay. So I have basically finished simple biasing and resistor divider biasing. Okay. So you can revise that from any book. So for those who are preparing for ESE, I've seen that like in my time, a lot of questions used to come from Cedra and Smith. Back exercise, like exact question used to come in the subjective exam. Okay, objective is pretty easy because there they will mostly repeat the previous year problems, but the subjective used to come from Cedra and Smith. And GATE, I have seen that they mainly follow this Razavi fundamental of microelectronics. If you follow this book, I think GATE questions will be very easy for you. Okay. Okay. Then let us start with biasing with emitter degeneration. So what we saw earlier was that the resistive divider network, the resistive divider biasing technique is not very effective, right? If there is a change in the resistor value R1 or R2, correspondingly VB can vary a lot. Okay. So then what happened was, even when the transistor was invented, okay, when the transistor was invented and people had to, use the transistor, they saw that this technique of resistor divider biasing, that is not effective. So from that time itself, when the transistor was invented, they started using the emitter resistance. Okay. Why emitter resistance? So this is very logical. Whenever resistor is used, the main purpose is because resistor follow Ohm's law. It is a definitive Ohm's law, right? Resistor will follow V equals to I into R, whatever happens. It is not an exponential relationship, it's a linear relationship, and therefore it's a hardware rule that the resistor will dissipate a power across it. Okay. So what happens is that we see that what we have to, you remember that in the beginning of the class we wrote 2 points, that we have to reduce VBE variation and we have to reduce IB variation. Beta variation, sorry, beta variation, right? Because beta will vary IC. So now you see that because of the R2 variation, R2 or R1 variation, what was varying is VBE, right? Because we saw this relation that IB was nothing but your VTH minus RB IB, sorry, VTH minus VBE by RB, right? So when I'm saying VBE is varying, then IB is varying. And we saw that we first assume VB, then we find IB, then we find IC, then again we find VB from the exponential relation, right? So once I find IB, I find IC, then again I find IC equals to IS e to the power VB by VT, and I find VB and I cross check whether I am close enough, right? And because of this exponential relation, if there is a variation in the RB value and IB changes by a small amount, the VB changes by a very big amount, or vice versa, right? So now what I want to do, I will try to make sure that if my, so now what will change with respect to temperature, two things will change. Either the BJT's beta will change or the resistor R. Now R variation is more prominent because of the temperature dependence, right? So suppose the beta variation is happening and correspondingly the external resistance variations are start happening. So first let us focus on external resistance variation. So what we will say that, okay, if my resistor variation is happening, then why not I dissipate that particular variation across another resistance. What I mean to say is that when I introduce RE, what I actually do is that now I make the dependence of VBE to what? It is VTH. This is VTH, right? This is VTH. So VTH minus IBRB minus VE. VE is the voltage across RE, right? So now you see that any change which comes because of the R2 will be first absorbed by RE. Why? Because that is an Ohm's law dependence. The power has to dissipate there. It is a hardwire rule. I have hardwired the resistor. Okay. So therefore, our intention is to dissipate a part of that variation across RE so that the part of variation that goes across VBE is small. Am I making sense? So I am not saying that the entire variation will be dissipated across RE. I don't know that. This is a circuit. Its behavior will be dependent on various physical factors. But if I introduce a RE, then the current has to flow from there, and therefore any variation in the current, a part of it will be dissipated across RE. I hope I am making sense. That is the reasons of putting RE. Now you will see this question in your GATE exam or any other exam. You will see that it comes in theory type of questions. You will see emitter resistance is used to make the circuit more stable. You go and check, you will find this line. And this is true. The presence of emitter resistance makes the circuit more stable. Stable against what? Against VB variations or beta variations. Because beta variation will vary IC. IC variation will vary VB. So IC variation, any variation, IC has to cover this path, right? So IC goes through RE. And the variation, a part of it has to get dissipated across RE. So any variation across RE, I don't care, right? That is the voltage dissipation across RE, that is the power dissipation across RE. It won't affect my region of operation. Okay. So now with this background, let us quickly write. So I have already written the equation, but I will again write it. Okay. So now your VE will be nothing but the power that is dissipated. So VTH minus IBRB minus VE. Now you see that since there is again emitter resistance across which power is dissipating, now the base current will be smaller than before, right? The base current is now smaller than before. So therefore in this case the assumption of negligible base current is more prominent. Assuming, so if you assume negligible base current, if you make the circuit such as the base current becomes negligible, V will be equals to VTH minus V, or I can say that the emitter dissipation is equals to VBE minus VBE, right? So in the earlier example, the 50 millivolts difference that we took, if you remember, 800 millivolts we used to take as VB, then we took 750 millivolts. So that 50 millivolts is now what is dissipating across VE. Okay. So now what is IE? IE will be nothing but V by RE, right? So now V I can write as 1 upon RE into VCC into R2 by R1 plus R2 minus VB. Okay. So now how can this result be made less sensitive to VB variations? Because now you can see that there is a dependence, right? So if the voltage drop across RE, okay, if it is large enough to absorb the variation, okay, so then the IE or IC is approximately constant. Okay, so if this difference is large enough, okay, then this the volt so the volt this difference is nothing but the voltage drop across RE, right? So difference is nothing but the voltage drop across RE. So if it is large enough, then the IERE will be able to absorb most of the variation. So to make this point more clear, because what I am speaking is right now, I don't know if it is making sense to you. So we will now see an example, and we will see that a variation in resistance value, how it does not affect the VC and VB. Okay. So please quickly look into this once, and then we will solve the example. And since we have put the RE value, I think it will now make sense to you that the base current automatically becomes very much negligible than the main current. Okay. Please let me know once you are done with it, then we will start with the example. Once you do the example, you will be clear about this thing, how the variations are not happening. Let me know please when you are done.
Done, Manakadani.
Are done, right? Okay. So this is the question. Please note it down. And yeah. So this question is in two parts, okay, and similar kind of question can be expected in GATE as well, okay. And these questions make very good for numerical answer type. They are very good candidates for numerical answer type. So please note down the question quickly. Okay, so I'm starting then. So first is calculate bias currents for the circuit. Beta is 100, IS you know. So this part you know, right? What you will do? You will first find the VTH and RTH. Please tell me what VTH you are getting. So let me take this circuit to the next part. Okay. Beta is 100 and IS is 5 into 10 to the power minus 17 amperes. Always remember that mostly in question IS is given in amperes, and that's where you can mess up. In gate also that can happen. Okay, because when the circuit is in kilo ohms and volts, all the answers will keep on coming in milliamperes, and if IS is in amperes, you might make a mistake there. So be very careful. Okay, otherwise in numerical answer type it will mess you up. Okay, so yeah. So what is the procedure? Terming this as VTH. VTH is VCC into R2 by R1 plus R2, right? This is R2, this is R1. Tell me what you are getting. 0.9. Okay. Now you know that we assume VBE, right? So assuming VBE as initial guess 0.8 volts. Okay. Now assuming VBE as 0.8 volts, we are getting VE as 0.9 minus 0.8, 0.1 volt. Now a doubt can arise in your mind that in the previous question we had assumed VBE as 0.75, and I had told you that since RB is present there will be a dissipation, therefore I am not assuming 800 millivolts, I am assuming 750. In this question I did not do that because base current is already negligible, and if I assume it to be some value less, that value is what is dissipating across RE. So it is the same thing. If I now say that VB is 0.75, that means 0.9 minus 0.75, whatever value is, it's the dissipation across VE. Okay. Okay. So in that case, I was assuming that the dissipation was across RB, and therefore I was assuming VB as less. But now the dissipation is across VE. So I am assuming VB to the same, and I am finding out the dissipation. Please don't get confused. So after this class, when you sit and work it out, you will understand what I am doing. Okay. VE is 100 millivolts or 0.1. So now what if V is this, RE is given. Now the question becomes simpler. IB is negligible. Okay, and V and RE you have. So IE equals to IC will be nothing but 0.1 volt by 0.1 K, 1 milliampere. First part. So I should have annotated it, but I took for granted that you must have known. So IC, and this is IC equals to IE because IB is 0. Okay. Okay. So IE equals to IC is 1 milliampere. Okay. So again the same thing, IB is negligible means IB is negligible with respect to the main current. So since it is negligible with respect to the main current, I can take it to be 0. You understand? It is not actually, it might not actually be 0, because if you divide by beta, whatever comes is the actual IB. But that IB, which is IC by beta, it is very less than I main. Therefore we take it to be 0, and therefore the dissipation across it will be neglected. Okay. So now when you get IC as 1 milliampere, we check the assumption of VBE, right? So VBE is VT natural log IC by IS. Please put in the value. Tell me what VBE you are getting. IS is 5 into 10 to the power minus 17. Please tell me what value you are getting.
0.796.
0.796. Good. So now you see, now you again cross check. Okay, now VB is 0.796, right? And what was the VTH that you found? VTH was 0.9 volts, and we had earlier done 0.9 minus 0.8, 0.1 to be VE. But now what is VE? V is 0.9 minus 0.796, which is 0.104. And now if you find IC equals to IE from this, you will get 1.04 milliampere. So you see, now there is no difference, not much difference. In earlier case, the difference was huge because we had to enter the, because the VB value which was changing, the RB/IB value which was changing the VB, that was coming inside the exponential term, and that's why it was amplifying. You know how an exponent works, right? Right? Exponent graph, you know, right? How it goes. So the, and the linear graph, how it goes, right? So since now the dependence is all linear, now inside the exponential, the RB/IB term is not there, right? And therefore you are seeing that the variation, the 4% variation of VBE does not affect your collector current much, okay? Because we have made the IB negligible, and we have made the IB negligible with the help of the emitter resistance, okay? Now determine whether it is in active mode or not. So VCE you find, VC is VCC minus ICRC. Tell me what you are getting. IC you take as 1 milliampere. So this 1.04 is, I am checking it, okay? So your actual answer has come. VB 0.796 and IC 1 milliampere, your actual answer has come. 0.796 or 0.8, it doesn't matter, you can take 1.04 also, okay? So VC you will get somewhere around 1.5, and that is greater than your VBE, therefore it is an active mode, okay? Now check whether the assumption of the negligible base current is correct or not. That will be the second step. So first go through this whatever I have done, and then we will go to the second step. So please let me know once all this is done and you are clear with whatever I am talking to, okay? So you would be seeing that the main purpose is to make base current negligible. Now I cannot make base current negligible just by saying it, I have to make the circuit in such a way. So in the first method we had seen that R1 and R2, if we make a choice properly, it will make sure that the base current is negligible. But what may happen, because of the temperature variation, because of the heating of the resistor, the value of R1 or R2 may change. Once the value of R1 and R2 changes, the assumption of base current negligible may not be fulfilled. Therefore, that circuit is not reliable, right? And if the base current is not negligible, then we saw that even the resistor divider network is not a good network, it is a very bad network, right? Because a small variation in R1 or R2, that will lead to a huge variation in your this IC collector current, right? And since it appears across an exponential, the VB again changes a lot. So the variation of R1 or R2, that will lead to a variation of VB, beta, and therefore the transistor can come out of the active mode of operation. Now since this is the problem we identified, we thought what we can do to make this entire circuit independent of the variations, right? So we saw that if we introduce an emitter resistance, if we introduce an extra resistance in the emitter, this current, the base current IB, that can be made negligible because the extra dissipation because of the variations, okay, variations of the resistor value, that can come across as a dissipation across the RE, okay. that will come as a voltage across RE, and therefore my base current will remain negligible. So this is so far consider the best circuit, best stable circuit. Okay, the stability factor is highest in this. So the emitter resistance is usually incorporated to make the circuit more stable, to make the common emitter amplifier circuit more stable. And there is a, since everything has a pros and cons, and in analog, if something is gives you some profit, you have to compensate for that as well. Okay, so the compensation is, in amplification the gain actually reduces, but we have methods for that also. We will see that in amplifier section. Okay, so as of now you can understand that the common emitter amplifier with resistor gives you the best possible stability. Okay, so till now if it is done, then we will solve the second part of the question. So the second part of the question was, how much does the collector current change if R2 is 1% higher than its nominal value? So now we will see what happens if R2 changes. Now if R2 changes by 1%, then what is the new R2 value? 9 plus 9 into 1 by 100, 9.09 kilo ohms, right? Clear? So now you see what is your new VTH. New VTH is 9.09 into 2.5 upon 9 plus 9.09. Sorry, 16 plus 9.09. Tell me what is the value you are getting. I am solving the second part of the question. Okay, so if R2 changes by 1%, what happens?
0.905.
0.905. Okay, or 905 millivolts. Now the earlier VTH old was 900 millivolts. So what is the difference? 5 millivolts increment is what we saw. Now this 5 millivolts increment will disturb the operating point or not, that is what we have to see, right? So we assume that this 5 millivolt has directly come across RE. Okay, and why can I assume that? Because I have made the circuit in such a way that base current is negligible. So if base current is negligible, then this 905 and this is negligible, this is 0, and this is VBE, right, and this is V. So I am saying that this 5 millivolts, it has directly come across this. Now you can say, ma'am, this can also come across VBE. You can say that okay, base current you have made negligible, this is 0, I understand, but VBE is there, right? So it can come across VBE. So that is what you have to remember. I had told you earlier that resistance follows Ohm's law, right? Its relationship with voltage is linear. So whatever change is there, it first comes across resistor, it will show. That is why it is used. It is a hardwired thing. It will definitely come. Its relationship is with voltage is much stronger. Okay. So therefore, this assumption is pretty much correct. Okay. So although the variation can also come across VBE, but the variation across resistance is stronger than that. That is what I mean to say. Okay, that's why with resistors, uh, if we ever go into MOSFETs, this will become more clear. Okay, so always remember that the relationship of a resistor is from with Ohm's law, that's why it's a very strong relationship. So any change in current appears very strongly across a resistor. Okay, so I am assuming that the 5 millivolt variation comes across the resistor. So if it comes across the resistor, then VE will be what? The difference will be 5 millivolt by 100 ohms, right? That gives you how much current? This is 50, right? What will be the current value? 50 microamperes. Sorry, this should be IE. So this has now changed IC by 50 microamperes. Okay, so the emitter current is raised by 50 microamperes. Now this assumption that the entire thing has come across the resistor is equivalent as saying VB is constant. Okay, which is reasonable because this will mean that it is only changed by 5%. Okay, so it was 1000 microampere at first. IE was 1000 microamperes. IE old. Now IE new is 1050 microamperes. Okay. And now if you put in the value 1050, if you put in the value and try to find out VBE, you will see VT log IC by IS, right? If you put in the value, you will see you are getting 0.797 volts. Earlier you had got 0.796, now you had got 0.797. So there is no much difference. So that's why VB is constant. Okay, so what I had actually theoretically, conceptually I tried to explain you, from numerical also you are finding the same thing. Is it okay? So the variation of IE, the variation of resistor that came directly across VE, which changed the emitter current by a small amount, when we put it in the logarithmic exponential formula, we see that the variation is not much. The VB variation is not that much, right? But in the earlier example, you had seen that it was a very huge variation was coming, right? Because in the exponential term, RB, IB came. Now IB is negligible. Therefore, the RB, IB is 0. And that's why we are achieving this. So, from numerical, I am actually explaining you the entire theoretical concept. Okay. So, please, it's my request to you that don't just throw it away after this class. Please go through these problems. Go through the book of Razavi also, and you will be able to understand it more. Okay. And try to solve the back exercise examples. So, please go through the numerical. I'm keeping it here. Please go through it, and after that we will solve another question. Okay, so I'm giving you 2 minutes to completely go over it. Okay, try to understand each and every bit, and then I will go to the next question, because the next question is a bit different. Okay, after that we will do self biased, which is the last biasing type. Okay, now let's move to a design problem. Okay, so if you have to design a circuit, how will you do it, right? So from where do we normally start when we are designing? Although it might not be directly related to the gate thing, but it's good if you just know it. Okay, so you can just typically write it. I will quickly write down the steps. So how we choose is, we decide on our IC. First we decide on IC by keeping in mind GM and RPI. Now from where you get GM and RPI? Your whoever wants you to design the circuit, he will give you a gain. He will tell you beta. He will say, okay, design for a beta of 100. Okay, now beta is nothing but GM into RPI. Okay, so from there the parameters GM and RPI will usually be given to you. So from GM and RPI you get IC. Okay, and you know the this I have told in the previous class that GM is nothing but IC by VT. Okay, so if you have GM, that means you have IC. Okay, now the next step is that we normally choose emitter dissipation of 200 millivolts. Okay, normally 200 millivolts is chosen. This value will change according to whatever your VCC value is, and VCC, remember, it is fixed. Okay, that is fixed on the basis of what process you are using to design a transistor. Okay, so typically for 1.8 volt or 2.5 volt of VCC, you use 0.2 volts, okay, as VRE. Once you have VRE, you know IC, you can decide on RE, right? Decide on RE. Okay, now this is done. Now what you have to do? You have to calculate VTH, which is nothing but VBE plus ICRE. That is VRE. So VCE plus VRE. So you normally take above 0.2 from VBE, and VBE you are getting from VT log IC by IS. So basically you know you will have the knowledge of IC from GM, and from there you can get the rest of the parameters. Now once you are done with this, you have to choose R1 and R2 such that IB is negligible. Now what does IB is negligible means? IB has to be very less than I main. And what is I main? I main is nothing but VCC by R1 plus R2. Okay. Now once this is chosen, from uh, rest of the knowledge of the circuit, choose RC, which is defined by transistor to be in edge of saturation. So you will have to make sure that your transistor VCB is greater than 0. That is VCE minus VB is greater than 0. Now VC is nothing but VCC minus ICRC. So this has to be greater than VB, and other values you know, from here you find RC. So that RC that you find from here will be the edge RC, right? So anything above that RC or anything below that RC, somewhat like that, you will get a condition we will see in the example. Okay, this will actually give you the maximum tolerable RC. Anything less than that RC will make sure that your device is in active region. Okay, so this is the procedure we normally follow if you have to design the circuit. Okay, so please quickly write this. I'm giving you 2 minutes. After that we will solve the last example, and then we will go to self biasing. Okay, so now let us come to this question. Design the circuit to provide a transconductance of 1 by 52 ohms. Let me write it again. 1 by 52, 1 upon 52 ohms. Okay, ohms is also in 1 upon 52 ohms for Q1. Assume VCC as 2.5, beta is 100, IS is given. What is the maximum tolerable value of RC? Okay, so please start. First calculate GM is given. GM is given as 1 by 52, which is equals to IC by VT. Okay, take VT to be 26 millivolts. Tell me what is IC. Please note down the question and solve for IC. Tell me what IC you are getting. And once you get IC, find VBE with this formula. Till here, please do it. Tell me the answer and then we will proceed. Please write the answer in chat box. After that, we will proceed. Okay. Okay. So Jayesh has got it. 0.5 milliamperes and 778 millivolts. Okay, good. Okay. So now once you have this, I told you what was the design procedure that we have written. Just look into that. We will assume VE, which is equals to RE into IC, to be 200 millivolts, right? So from here you will find what? RE. RE will be 200 millivolts by 0.5 milliampere. Nothing but, what are you getting? 4 kilo ohms. Sorry, 400 ohms. 0.4 kilo ohms. 400 ohms or 0.4 kilo ohms. Correct? Yes. Right? So now after this is assumption, okay? I'll write it, otherwise you will get confused. Assume, because this is a design question. So design question, we assume that the dissipation is 200 millivolts. Now we want VTH to be VBE plus VE. Okay, and VBE we got a 778 plus VE is 200, that gives us 978 millivolts. Okay, so now VTH was nothing but what? VCC into R2 by R1 plus R2. That is coming as 978. And remember that we don't have R2 and R1 plus R2, right? So what we have to find it out, because it is a design problem. So R2 by R1 plus R2 is nothing but 978. This is in millivolts. So 978 millivolts upon 2.5 volts, right? So solve this, and what is the value of R2 you are getting? R2 by R1 you are, plus R2 you are getting you 5.
Point 3912.
Okay, so I haven't checked it, taking the word for you. So remember that IC you had got as 0.5 milliampere, therefore IB was 5 microampere, right? Beta is 100. Beta is 100. Okay, so since IB is 5 microampere, what you want is you want this IB to be negligible. That means you want VCC by R1 plus R2, which is the main current, to be very greater than 5 microampere. This gives you another condition, right? So R1 plus R2 has to be very less than 2.5 volts by 5 microampere. Okay. Okay. So now when I say that R1 plus R2 has to be very less than this value, we can take a factor of 10. Okay. So let us say that VCC by R1 plus R2 is 10 times 5 microampere. Okay. So this will bring you to the condition R1 plus R2 is 50 kilo ohms. You can check. Okay. And once R1 plus R2 you have got, you can put it in this equation and you will get R2 as 19.56 kilo ohms. And once this is found, R1 you will find by 50 minus 19.56, which is 30.44. So please, I am giving you 1 minute, just see whatever I have done. Okay, so assume I main is 10 times IB. 10 times is what we usually take. Okay, okay. So just look into whatever I have done. I am giving you 1 minute. After that, I will proceed. Any doubts till now? Anybody can raise the question. Okay, so once you have it, you now have everything in your circuit except RC, right? We have found RE, we have found R1, we have found R2. Okay, now for RC, what will limit RC? You know that VCE has to be greater than VBE, right? And in this case, VBE is defined by what? VTH minus VE, right? So basically VE you had defined, right? So VTH is what is actually supplying VE and VBE. So VCE has to be greater than VTH. Mainly this, if you satisfy, it should do, right? If it is greater than VTH, it is automatically greater than VTH minus VE. So we take the condition to be VCE should be greater than VTH, and therefore VCC minus RCIC has to be greater than VTH. Okay. Now you solve this. RCIC should be less than 2.5 minus what was VTH? We got a VTH, right? 978.978. So RCIC should be less than 2.5 minus 0.978 is 1.522. Okay, and IC you know, so RC should be less than 1.522 volts upon 0.5 milliampere. Okay, and this brings you to RC should be less than 3.044 kilo ohms. So RC maximum RC that you can tolerate is 3.044 kilo ohm. After that your device goes into saturation. Okay, if RC exceeds this value, the voltage, collector voltage will fall below the base voltage, and therefore as mentioned, the transistor will be able to tolerate only up to around 400 millivolts of VCB forward bias. Okay, so this is actually a different I will not go into that. So it is called soft saturation. So for low voltage applications, a bit greater value from this RC can be tolerated, but in your gate question, this is what will come. So RC max is 3.044 kilo ohms. It won't go beyond that. Okay, and this is a good question. This kind of question is expected. Please make a note of it. After that, we will start self bias circuit. Let me know when if we can proceed.
Please continue, ma'am.
Okay, so now two problems with this kind of circuit that we face is that you see that in the circuit, what I was saying is I main should be, where is the circuit? Okay, I was saying I main should be greater than IB for IB to be negligible. Now, what is the condition that makes I main high? When will I main be high? when these resistors R1 plus R2 will be low, right? That will only make sure that the entire current flows from here and it does not go inside the transistor, right? So what is happening, that for IB to be negligible, I main must be high and thus R1 and R2 should be small. So what is the problem with R1 and R2 small? So we will see when we see amplifiers that this value of R1 and R2 translates to a low impedance. Okay, so my iPad probably is not getting enough internet. Just one second. Okay. So this translates to low impedance of amplifier, which is not a good thing. We want amplifier to be high impedance, amplifier to have high impedance, because if amplifier has low impedance, then the signal that you have, any signal that you input to the amplifier, if it is having low impedance, it will go through the impedance, not to your amplifying circuit. Okay, if there is low impedance. So we will see that in detail when we do amplifier, but as of now you just take care of this, that R1 and R2 if they are small, then it results to a low impedance of the amplifier. The next thing is that if we choose a large VRE, okay, if VRE becomes high, because we are trying to dissipate the extra variation across VRE. So if the VRE becomes high, the margin for VCE is low. How? Because VCE is nothing but VCC minus ICRC minus VRE, right? So VCC minus ICRC minus VRE is your VCE. So therefore, if VRE increases, this drop will increase and therefore your VCE reduces. Now the reduction of VCE is limited by VTH. VC has to be greater than VTH. So this is a limitation. This is another limitation. Okay, there has to be a particular minimum value of VC that we saw when we were finding RC, right? Okay. So I'm not solving. There is one more example which shows this conditions that I showed, but I'm not solving that. We will straight away go to self bias stage. Self bias stage. So you guys please write it. I'm giving you 1 minute, and after that I'll start the self bias stage. Okay, so now coming to the self-bias stage. This is the self-bias stage, okay? Please draw it. Why is it called self-biased? Because the collector voltage VC is used to bias the circuit directly, okay? So it is called self-biased because base current and voltage. So basically biasing, what we are doing? We are basically biasing the base, right? We are basically biasing the base. So the base current and voltages, base current and therefore the voltages are provided by the collector. Okay, now this is an interesting circuit. Okay, why is it so? You see that now the voltage that is coming here, VBE, right? The voltage that is coming here, VBE, nothing but VCE minus IBRB. This is IB, this is IC, right? So therefore the current which comes from VCC is, please make a note of this. This circuit is also asked in GATE a lot. Okay, so VBE is VCE minus IBRB. And what is the condition for active region? Active region's condition is what? VCE should be greater than VBE, right? Now you see in this circuit, this condition is always true. This condition is always true. Sorry, this condition is always true. This one, always true. Why? Because VCE is what is actually giving VBE. So VCE minus RB. Unless you subtract the portion IBRB, that can never be negative, right? So IBRB will always get subtracted from VCE, and therefore this condition will always be true. Did you get the point? So VBE is VCE minus IBRB. Therefore VBE will always be less than VCE. Okay, and therefore this self-bias stage is always an active region, irrespective of whatever value of RB you choose. Okay, so now VCE is nothing but IBRB plus VBE. IB is nothing but IC by beta into RB plus VBE, right? And therefore you can also write IC as VCC minus VCE by RC, right? So IC will be nothing but VCC minus IC by beta RB plus VBE by RC. Okay, so now if you solve this, ICRC equals to VCC minus ICRB by beta plus VBE, IC common, RC plus RB by beta equals to VCC. Something I have messed up. Okay, this is minus. This is minus. VCC minus VBE. So IC is nothing but VCC minus VBE by RC plus RB by beta. Okay, please take a look into the derivation that I have done. So the calculations you see is pretty much straightforward, right? It is only KVL equations. Okay. So I assume that you have written it. So I'm moving forward. Okay. If you want more time, you can tell me. So with an example, we will now see what are the problems that can come. Okay. So now the example you take for a self-bias circuit. So this is a self-bias circuit. In the self-bias circuit also there can be a presence of emitter resistance. Those things can happen. Okay. But we'll see. So this is 2.5 volt. RC is 1K. RB is 10K. Okay. And other values are given. So now we will proceed assuming VB as 0.8 volts. Now we assume VB as 0.8 volts and we find IC. Tell me what is the VB you are getting, IC you are getting. Okay, so just 1 second, I made a mistake. So when we assume VB, we don't use the exponential term directly. So what we will do is, after assuming VB, I have these values, right? So I can apply a KVL here. Okay, so this is IC plus IB and this is IB. So I will apply a KVL 2.5, right, minus IC plus IB into 1 kilo ohm minus 10 into IB, 10 kilo ohm into IB, okay, minus VB is 0, right. So from here IC plus IB minus 10 times IB equals to 2.5 minus 0.8 VB, here you put the value of VB, okay, and IB you know it is IC by beta. So IC plus IC by 100, okay, minus 10 times IC by 100 equals to 2.5 minus 0.8 is 1.7. Now tell me what is the IC you are getting. You understood, right? We assume VB and then we put it into KVL. So mistakenly I wrote the exponential formula. That is not correct. We will use the exponential formula later again to verify VB.
One 1.531 milliamps.
Yeah, 1.531 you should get. So I think if you directly use the formula, you will get 1.545. I think I have mistaken somewhere in the equation because this is the formula that you should directly translate to. So let me just check once. Oh, this is also wrong, whatever I have written. So yeah, this is the formula it should translate to, not this one. This is the formula, you can directly use it also. Okay, so if you put the values of RC, RB, there you will directly find the value. Okay, so one thing I forgot to mention, that here they have for the cell bias also you have to consider IC as um, very greater than IB, so that when you take the current from here, in the book they have mentioned this as IC directly, okay, because they are taking IB as negligible, but I think this will also do. So I think if you take it IC plus IC by 100 minus 10 times IC by 100 equals to 1.7, that is what we are getting, right? Please verify this KVL once. This is correct, right? This equation that I have written, please check it once. If we don't neglect base current, the derivation that I have made was assuming base current negligible.
Ma'am, in the second step, IC plus IB plus 10 IB will be getting 1.
IC plus IV. Yeah, right. Okay. Okay. So now what is coming? So 1 plus 10 by 100 plus 0.01 is, yeah, 1.53. And if you neglect the base current, you will get 1.545. Okay, so it is fine. Okay, thank you. So IC is 1.531 milliampere, and once you get it, you can verify VB, which is VT log IC by IS. So we start from assuming VB, we find IC from the KVL equation, then we put IC in this logarithmic equation, we find VB. Now if you find VB, you will get 0.026 natural log of IC is 1.531 upon IS is 5 into 10 to the power minus 17 ampere. Okay, so you get 0.807, which is very much close to 0.8. Assumed VB was 0.8. Okay, it is almost the same. Okay, right. So the initial guess of VB and the value of IC is reasonably accurate. Okay. Now you should remember that this variation you actually have to compare with this value in the numerator, right? So any value variation in the value of VBE, right? So say delta VB. So IC will be equals to VCC minus of, let's say, VBE plus delta VBE upon RC plus RB by beta. So for a self bias circuit, what will happen is that IC equals to VCC minus VBE, which is your previous numerator, minus delta VB by RC plus RB by beta. So as long as VBE VCC minus VBE is very greater than delta VBE, your circuit is okay, right? As long as this is satisfied, self bias circuit is good. And normally this variation will be very low, right? So suppose if VCC is very low itself, then this problem will come, because in that case delta VB might increase. But as long as this condition is satisfied, your self bias circuit is good to go. Okay, so please have a look. Giving you 1 minute. After that we will quickly see the PNP and then finish the class. Okay. So two conditions we saw for self-biased circuit. I am just writing down those two conditions. Okay, self-biased. So we had made some notes after each biasing scheme, I think. So self-biased condition is that VCC minus VB should be much greater than the uncertainties in the value of VB. Okay, and the second is RC must be much greater than RB by beta to lower the sensitivity to beta. Okay, so if RC is very greater than RB by beta, then you will see that the derivation that we did will come to an approximation made by this, and you see that it is completely independent of RB, right, which we are trying to make. In all the biasing circuits, that is what we are trying to do. We are trying to make it independent of RB. Let me make the font a bit greater. Okay. Let me know once we are done with this. Okay, we'll start PNP. Okay, so let's continue to PNP. So PNP only derivations we will do. I am not doing any numericals. Okay, but from the derivation itself we will understand how to apply KVL to a PNP transistor. And as I keep on mentioning, please make your networks and signals and system very good. Okay, first you should do networks and signals and system, then only touch other subjects. Networks and signals and systems is a must. Okay, okay. So now PNP. First is simple biasing of PNP. Okay, so this is a simple biasing circuit of PNP. You remember what was the simple biasing of NPN? Sorry. So this was the simple biasing of. Now the difference between PNP and NPN is all with respect to ground, what voltage you have to apply, right? This is NPN, this is PNP. Okay, in PNP this is the emitter resistance. So you see that is connected to VCC. In NPN, the emitter is connected to ground. That is connected to VCC, the highest voltage node. And VEB is always positive. In NPN, VBE is positive. So you have to just keep that in mind, which is positive. And VEB, just the opposite, this is positive. Here VCE is positive. Here VEC is positive. Here VCB should be greater than 0 for reverse biasing and active region. Here VBC has to be greater than 0 for reverse bias active region. Okay. And how do you remember this? VCB is nothing but VCE minus VBE, right? And how do you remember that? So VCE is VC minus VE minus of VB minus VE. Okay. So okay, my network is again poor. Just wait for some time. Yeah. So VC minus VE minus VB minus VE. That is how you come to VC minus VB. You got it? Right? And this has to be greater than 0. So if I say VBC, then VBC is nothing but VEC minus VEB. You see? VE minus VC minus of VE minus VB. And this has to be greater than 0 for NPN. So please write down these two conditions, and then everything is sorted out in PNP. Now you can solve any question. Okay, you only need to know how to apply KVL. That's it. Please let me know if you are done. We'll have to make it quick now. And how is this VEB or VB is written? So you see the direction of current. Okay, the direction of current will follow the direction of arrow. So here the direction of arrow is this, so the direction of current is like this. Therefore, this is positive, this is negative. The one where the current is entering is negative terminal. So this is E, this is B. So E is more positive with respect to B. So VEB is positive. Okay. And here the direction of current is like this. So plus minus VEC. VE is greater than C. So VEC. Okay. I am assuming you have written this. And now I am going to the KVL of this circuit, KVL equations. I am directly writing it. Okay. So you will get IB as VCC minus VEB upon RB. Okay. This is the first current equation, and therefore IC will be beta times IB. Right, and RC max will be given by VCC minus VEB by IC, and everything else is same as the analysis, same as the NPN. Okay. Okay, so now for the resistor biasing, divider biasing, again determine IC and maximum allowable value of RC. So what will happen? I am doing the Thevenin equivalent part itself. So the Thevenin equivalence of this circuit okay, and therefore IB is equals to VCC minus VThevenin minus VEB upon RThevenin. This is VEB plus minus VEB. Okay. And once you put in the value of VThevenin, you find once you put in the value, you will get R2 into VCC by R1 plus R2 minus VEB by RThevenin as IB. And IC will be beta times IB. All other, everything else is same, you just the VB is changed. Okay. Please have a look. After that, I'll show you the self-bias circuit. Okay, so I'm moving forward. Okay, so with resistor divider biasing, we had seen another circuit, right, with the emitter resistance. So here also the same thing will happen. Okay, similar circuit. Okay, and here with the assumption IB is very less than I1. I1 is from here. This is IE, this is IC, this is IB. Okay, so IB is very less than I1. We have VTH as VCC R1 by R1 plus R2. Okay, and also the value of IE will now be VCC minus VTH minus VEB by RE, right? And now if you put in the values, you will get VCC into R2 by R1 plus R2 minus VEB 1 by RE is IE. Okay, and from here if you solve for RC max, I'm just writing it down, you guys should do the derivation and check. RC max will come out to be RE into VCC into R1 by R1 plus R2 into 1 upon R2 by R1 plus R2 into VCC minus VEB. Okay, so please try to come to this point. Okay, so just see the derivation that I have done. Don't know whether you will be able to see it or not. Okay, please go through the derivation. After then the self bias circuit is left. Okay, and then we will be over the biasing. Should I go to the self bias circuit? So if you understand the NPN, this will be okay for you. Okay, so I'm going to the cell bias circuit. I'm quickly covering that up. So yeah, so this is the self bias circuit, and as we have seen, this will be your IE, this will be IB, and therefore this will be IC. IE again, this will be IC. Okay. Now here your VCC will be equal to VEB plus VTH, or let me say that this is Vx. Okay, this is Vy. So VEB plus Vx for VEB plus RBIB plus ICRC. Okay, and here VEB plus RB by beta, the same thing, plus RC into IC. So RB by beta, if it is very less than RC, then it is completely independent of RB. Okay, and the Q1 is always in active mode. You can check that. Let me take this to this side so that okay. Now I think the entire thing is visible. Don't know how much it is clear to you, but entire thing is at least visible. Okay, so take a quick note of all this, and in the next class we will start the bipolar amplifier. Next class will be of 2 hours whenever we conduct the class. Most probably I will conduct it next Saturday itself, but after that, so next Saturday is I think 22nd something. Next Saturday is 21st. So I will conduct the class on 21st. Till now I don't have any appointment. In case I have an appointment, please try to log in into the class. If I am not there, then I will not, I cannot let you in obviously, or I will inform the NPTEL team also, they will make an announcement. And 28th I cannot take a class, I already have an appointment. So next class I will take 2 hours. Okay, and that will finish the next class stuff also. We will start with bipolar amplifier. Okay, and C amplifier will completely see. Although we have done the small signal analysis of C amplifier, but I will give a quick overview and then I will solve some trick questions. Okay, so please let me know if you guys are done, then I will stop the screen share. Okay, so any questions on this? Please solve this problem, solve these circuits and try to solve a few problems from the book also. Okay, okay then, thank you.